are going to look at an inclined plane scenario with friction. If we want, we could look at how to find the coefficient of friction, whether it's sliding or whether we're looking at static or kinetic friction. So we're going to look at those scenarios. First, let's look at this this box here. We have a box that is on an inclined plane, and the first thing we want to do is draw the forces that are acting directly upon that box. So the first thing we have is we have a force acting down. That force is not circles, but rather that force is, so we have the force of gravity acting down, which is equal to mg. The force of gravity and mg are in fact one and the same, right? So we have that. That is always going to be a force acting on that box, no matter what. And we typically will draw that acting from its center of mass. Remember, just like how we showed from the meter stick, where we have a torque situation happening from the meter stick, where we're trying to balance each side of the meter stick, we act from the center of mass of it. So we always try and go from the center of mass, especially when it's a gravity effect, because we basically say that on average it's acting from that location. What else do we have? Well, we have, at minimum, we also have a normal force acting upon it as well, and that is going to act perpendicular to the plane. I could put that arrow there if I really wanted to, and I can say, hey, it's a 90-degree angle. I don't have to necessarily put that in there, and I don't necessarily have to go from the contact point, but technically speaking, that's where we can say that the force is originating from. But typically we go away from the object. That's the way we draw the forces, is going away from it, not towards it. And so at minimum, we have those two forces, because there doesn't necessarily have to be friction. It could theoretically be frictionless, at which point it would in fact be accelerating down the plane if there was no friction. How do I know it would be accelerating down the plane? Well, if I take these two forces, here's the nice thing about having the smartboard, is this is actually the appropriate length of those two forces. The reason being is because if it were to slide down the plane, it would in fact slide down parallel to the plane, right? That would be the vector addition of those two forces. In fact, in red, I just drew, if there was no friction, I just drew in red what the net force would be. This here is the net force. I go from the very beginning to the very end, and I just drew these two forces together to tail vector addition, where from the tip of one, I put the tail of the next, and then when I'm done, I go from the very beginning to the very end. That is my vector addition, and that would be my net force if there is no friction. And so, since it's accelerating, I can say that this force here, whatever the net force is, that would be equal to ma acting down the plane. Okay, so there we are so far. But there may or may not be friction. Let's also say that we're going to kind of do a little something weird here, where we're going to say that this is the y direction and this is the x direction. I know that seems a little bit weird, but we're going to kind of tilt our head as we look at this problem. And let me go ahead and put this back up there. So we're going to say that the normal force is actually acting in the y direction, and the force of gravity is not. The force of gravity is somewhere in between. What we're going to do is we're going to break the force of gravity down into its components along the x and y direction, the x and y direction that we just made up. So let's go ahead and do that. Let's go ahead and break down the force of gravity into its y direction, which looks something like that, and its x direction. And I should have those. There, it's drawn a little bit better. So I've got the normal force. Let me put a label that. The normal force is going to be opposite of the force of gravity in the y direction. So here is the force of gravity in the y direction. Those are opposite of each other. In fact, what can I say about their magnitudes? They're equal. They're equal in magnitude. How do I know that? Because if they weren't equal, this thing would be falling through the plane, or being pushed up out of the plane. But since it's not accelerating in this direction whatsoever, it's only moving this way, at least potentially. Therefore, there cannot be any, the forces in that direction must be balanced. So we know that those two forces are equal and opposite. So we can say that the normal force is equal to the force of gravity in the y direction. In fact, wait, here, let me express that differently. Let me really start from scratch and express it from scratch the way it should be. I'm going to say that the net force, or otherwise shown as the sum of forces in the y direction, is equal to, let's say that the sort of upwards to the right direction is a positive direction. So the normal force minus the direction of the force of gravity in the y direction. Because if the force of gravity in the y direction would be acting in a negative direction relative to the normal force, and that those two added together gives us a net force of 0. That's where it originates. And so I don't really need this part anymore. I just use that to start my expression. And I could add the force of gravity in the y direction to each side of the equation. So that's where I get this from. I can say that that's why the force, the normal force, is equal to the force of gravity in the y direction. So those are equal and opposite. That's where that comes from. Okay, so once we've expressed that, let's also look at this force here. We have a force of gravity in the x direction. That force of gravity in the x direction, if you notice, remember if there is no friction force, then the force of gravity in the y direction is that net force that we were talking about earlier. If there is no force of friction, and we can get to that a little bit more later. First, before we get into that, let's look at how we can find the value of the force of gravity in the y direction and the value of the force of gravity in the x direction. Well, typically, we're going to be given an angle. So this is usually the angle that is expressed, angle theta. So the inclined plane is risen off the horizontal at some angle theta. Okay? Well, I wonder, do you recognize that this angle here is also the same angle theta? Those are the same angle. These are both right angle triangles. If you notice, in fact, if I were to bring these down to this point here, just that way we're acting at the transition point between, or the contact point rather, between the inclined plane and this triangle. What I can say is that this is a 90-degree angle as well. So if this here is 90 degrees, the last one that I drew, if this is 90 degrees, here we have angle theta, here we have a 90, so therefore this one in here must be some other angle. Let me in fact call that alpha. And if this is 90, if this here is alpha, then this one here must be theta. A little bit of geometry. It's like, oh my gosh, there's so many angles. I know, that's the complicated way to figure it out. Like, which angle is which, and that's the complicated way to figure it out. Hopefully I didn't go through that too quickly. You can look back at it a little bit more later if you want. But I can simplify it a little bit. Here's the way I look at it. Here's honestly the way I figure that out. Here's angle theta. Okay? I know that if this is a right triangle, and this is a right triangle, and this is a right angle there, therefore one of these two angles here must also be angle theta. I know that. Which one is it, though? Here's the easy way to figure it out, is that if I look at this angle here, when this angle increases, let's say that the incline of this thing increases, and this here must stay at 90 degrees. They must stay perpendicular to each other. If this angle increases, which one of these two angles also increases? You kind of have to picture it a little bit. which one would also increase? One of them would get bigger, one would get smaller, and that's honestly the little picture that I put in my head to figure out which one of those two angles is theta. Now, in this particular scenario, you can just memorize, hey, this angle here is always going to be theta. But in other scenarios, it won't always be so clear. Okay? With the inclined plane problem, it's going to always be this angle here. But I'm just trying to give you guys some tips on how you can figure out which angle is which when you move to other things sometime off in the future. So that's my trick, is I just look, hey, which angle is going to be also increasing? It must be the same angle. So after all that, that's angle theta. Bottom line, that's angle theta. So therefore, if that's angle theta, and I want to find the force of gravity in the y direction and the force of gravity in the x direction, here, let me drop this down, then if I know any trig, then I can express these two things in terms of theta and mg. Remember, the hypotenuse of this triangle is mg. So if I'm looking at the opposite side of the triangle here, I'm looking at the opposite side of the triangle. If I'm looking at the opposite side, I'm going to use sine. So I'm going to go from scratch here. I'm going to say that the sine of angle theta, remember SOHCAHTOA, right? SOHCAHTOA. So I'm using the sine of angle theta is equal to the opposite over the hypotenuse. Well, if that's true, then that means that in this case, it's going to be equal to the force of gravity in the x direction divided by mg. And so if I multiply each side by mg, I would get that the sine of angle theta times mg is equal to the force of gravity in the x direction. Let me take this and shrink it down just for a reference, and I'm going to bring this back up here. All right, so that's my little reference on how I got that. I'll put it off to the side. But this here is my force of gravity in the x direction. And then I'm going to do pretty much the same thing to find the force of gravity in the y direction, this one here. So with that, do you recognize that it's pretty much all the same procedure, except now I'm going to use cosine, because it's the adjacent angle. So the force of gravity in the y direction is equal to cosine of angle theta times mg. And it's really quite the same procedure, except I'm using cosine rather than sine. Otherwise, it's the exact same thing. So I've expressed the force of gravity in the x and the force of gravity in the y direction in terms of mg. Remember, this is also equal to the normal force. That is helpful in the future. All right, so remember that from here I had said that if there is no force of friction, that the force in the x direction would be all of the force along the plane, therefore the force accelerating it. Because what I can do is I can say that the sum of forces in the x direction now, I did the y direction before, now I'm doing the x direction, the net force in the x direction is going to be equal to the force of gravity in the x direction minus any force of friction. So now I need to look, okay, is there a force of friction? If not, then this is the same thing as sine theta times mg, right? Or if there is a force of friction, okay, I just keep that force of friction in there. But wait, remember that the force of friction is equal to mu, let's say it's sliding, okay? Mu k times the normal force. And so I take this and I substitute that in for the force of friction. So mu k times the normal force. Oh, wait! There's more! The normal force. What's that equal to? Cosine theta mg. Let's rewrite that so that we can express that. So the sum of forces in the x direction is equal to sine theta mg minus mu k times, again, we're saying that the normal force is equal to cosine theta mg. So we're just breaking it down and substituting. So if there is friction, then it's causing it to slow down. You should recognize that this force will be either equal to or larger to this force every single time, because it's not going to just magically start sliding up the plane. That'd be pretty weird. I would probably wee myself just a bit. All right, now let's say that rather than this being kinetic friction, what if I then say it's static friction instead? What if it's static? That means that it's not sliding, right? That means that it's not sliding, it's not accelerating. So therefore, let me grab all this and move it over just a little bit. Because, in fact, hold on, let me backtrack. In your notes, you've probably already got this. Do you recognize that I have to put another equal sign here? Because if it is sliding, if this force is larger than this force, that means that it is accelerating. Not just sliding, accelerating. That means that this is all equal to ma. Its acceleration down the plane in the x direction, it is accelerating. If it is sliding, and if this force here is bigger than the friction force. But, just to simplify things, let's say that it's not accelerating. So I'll rewrite it. Sum of forces in the x direction is equal to sine theta times mg minus mu s. So I'm talking about static friction. It's not sliding. It's not moving. Times cosine theta mg is equal to 0. Because it's not accelerating, right? The ma is 0. The acceleration is 0. Therefore, the whole thing's equal to 0. Again, I just need that to start this whole business. So since this is equal to 0, what I can do is I can add this to each side because it is equal to 0. I'm not able to really do that so much in the case above. So I'm simplifying it here a little bit. Sine theta times mg equals mu s cosine theta mg, because each of these two sides was equal to 0, therefore I can add each side by mu s cosine theta mg. Now, I'm going to divide each side by cosine theta mg. I'm going to solve for the coefficient. So, in fact, I can say that the static coefficient of friction is equal to sine theta mg divided by cosine theta mg, which is equal to what? Look at this. Mass cancels out. Is it not the same mass? It's just sitting there. Does the mass change? No. Gravity. Does it change? No, it cancels out. Sine theta divided by cosine theta is equal to tangent theta. So the coefficient of static friction is simply equal to tangent theta. I don't need to know anything else except for the angle. And what I do is I basically take an inclined plane and I continue to raise it. I continue to raise it until I get to the point where the block just starts to slide. If I measure the angle at which the block just starts to slide, at the moment that it just starts to slide, that would give me my angle theta, and that would then in turn give me the coefficient of friction, static friction. If I were to then, however, if I wanted to find the kinetic friction instead, let's say I did the same procedure, but rather instead I allowed this block, let me go change the color of the block. If I instead allowed this block to slide down, so I increase the angle of this thing here, and I allow the block to slide down. So as soon as it starts to slide, I'm going to have to actually decrease the angle because it's harder to get something moving than it is to keep it moving. So once it starts sliding, I decrease the angle slightly, and I make it just the angle so that way it just barely continues to move down. It's sliding, but it's not accelerating. It's not accelerating. Do you recognize that the acceleration up here would be 0 again? But now I would be looking at, rather than static friction, it'd be kinetic friction. Again, it would turn into tangent theta. The experiment's slightly different, but the math is the same. It would still be tangent theta. That would give me the coefficient of kinetic friction in that case because it is sliding. It would be a different angle. The angle would be less if I did that experiment. And so that is, in a nutshell, about as quick as I can go through it, the friction acting along a plane. We have, to recap, I have a force of gravity acting down. I'm going to always have it. So I break it down into two components, perpendicular to the plane and parallel to the plane. Remember that the one that is perpendicular to the plane is equal and opposite to the normal force. And the one that is parallel to the plane is equal to the force of gravity in this direction, the one trying to pull it down the plane. We can say that the cosine of angle theta times the hypotenuse is the perpendicular to the plane, while sine theta times mg is the one that is parallel to the plane. And then I can look at the sum of forces in that direction along the plane. In fact, this is really the better one for me to star because I included MA at the end. Is it accelerating? Is it not? That's something you have to look at. So that is in a nutshell. All right, you can go back and look at it. Hopefully that helps.